Hello everyone. Today we're going to talk about system properties in signals and systems. So the three properties that we're going to look at today are memoryless, causal, and BIBO stable. Essentially, memoryless is when a system does not, the input of the system yields an output that does not depend on the past or the future. So it depends only on the present. That's why we have whatever the system goes through, whatever input it has the same output. Okay? For causal systems, it can depend on the present or the past, but it can't depend on the future. And lastly, for stable, we essentially just assume that we have a bounded input. So let's say t is less than or equal to a, and then we see if our output is going to be less than infinity. So output has to be less than, it has to be finite essentially. So let's do some practice problems. Okay, so for each of the problems that I wrote, try to determine if the system is memoryless and or causal. So pause the video, try to do it, and I'm going to write the solutions. By the way, the standard notation for a function transformation is this. This is like a conventional operator. So you know how, let's say you could have t and then you take x, okay, and then you get x squared plus 1 as a function. We call it f of x, right? And that's usually how functions work. So functions transform variables. Well, systems, so when we do h, this is calling a system. Systems transform functions. They don't transform variables, they transform functions. Okay? It's a little bit of theory. So for part A, the system is not memoryless. Okay? Why? Because it depends. So for, let's say for t0, output depends on past and present, because we have negative infinity, t0 to t0. So our function is evaluated from the past all the way to the future. So it is definitely not memoryless. Here, I'm going to move these down. Okay. Is the system causal? Well, again, it is definitely not memoryless, but for causal, we can accept the past value, so from negative infinity all the way to t0. But the fact that we're evaluating into the future it causes the system to not be causal. So it is not causal either. Okay. Let's solve part B. So part B is here. Okay, this system is not memoryless because for a given input, xt, we're depending on the past. We're depending on a previous value. So it's not memoryless. And for causal, it is causal. Why? Because for any t0, so for any given input, t0, okay, so x of t0, we get a value from the past, so t0 minus 1 plus 1. This plus 1 does not matter, okay? We only need to look at the other x of t's, how our function was transformed. And because it was transformed in such a way that we only care about a past a past value of the function, then the system is causal. Okay guys, for part C, we actually have to solve the integral first. So here, we see alpha is equal to 0, so we can immediately evaluate the function x of tau and just say x of 0, take it out of the integral, and we have from negative infinity to t of delta tau d tau. So this is just going to be equal x of 0 u of t. Okay, if you wonder how I got the u of t, you could probably just look it up to understand how the area of the delta function is just equal to 1 after t equals 0, and before 0 it's just 0, so that pretty much defines the unitary function. Yeah, so x0 u of t. Now, is the system memoryless? No, not memoryless. Why? Well, because if we have, for example, x of 1 as an input, then our output is just going to be x0, and then u of 1 is just 1. So this is just going to be x0. And because we could clearly see that the present input depends on the past, the system is not memoryless. Now we need to check if the system is causal. So the way we're going to verify is we have to cover all of t, all negative values and all positive values. So let's see what happens when t is less than 0. Well, we're going to have x of t that's going to give us 0. So the system is just going to give us 0 because the unit function is always going to be 0. And since we're multiplying our unit function by x of 0, it's always going to give us 0 times x of 0. Okay, so this is just equal to 0. So far it's causal. But now, if x0 is greater or equal than 0, then for any input x of t naught, we're going to have x of 0 times 1, which is just x of 0. Right, so this is going to be, the system is going to be causal because all the values of t0 can only be greater or equal to 0, which makes the system only depend on the present and past values. Okay, so what I mean by that is, for example, let's say we have x of 5, we're going to get x0 as the output. So we could see that we're depending on the past value. And if we get x of 0, then we're depending on the present. So yeah, that's it for this problem. Let's move on to part D. Okay, this problem is probably the easiest because we're going to have tau as, or we're going to have alpha equals to t in this case. And so this entire integral is just going to be x of t integral from negative infinity to infinity of the delta function. And whenever you have integration of the delta function from negative infinity to infinity, it is always equal to 1. So all this is just equal to x of t. So we can clearly see that the system of x of t equals x of t. So the system is memoryless. Now, is it going to be causal? Yes, because it's always going to depend on the present. For all t naught, okay, we're going to have x of t naught, and it's going to give us, as the output, t naught, x of t naught, after it goes through the system. So it is causal. Alright, now let's solve some problems on BIBO Stable. Pause the video and do it yourself, and I'm going to write the solutions. Okay, so for part A, we assume x of t is less than or equal to a, and we're assuming that a is our bounded input. Now what's going to happen is we have h x of t, okay, equal to 1/2 a squared plus a. And then the second step is we take the limit as t approaches infinity of h x of t, and we get 1/2 a squared plus a. So this system is less than infinity on the right side of the equation, so it's BIBO stable. Okay, and we just keep on doing that for every problem. So for part B, I'm just going to bring it down a bit. X of t, let x of t be less than or equal to a, and so we get h x of t equals 1 over a, and now we take the limit as t approaches infinity of hx of t, and we get 1 over a, so it is stable. Stable. Part C, again, x of t less than or equal to a, and it's important to write this step even though it's repetitive. You have to write your assumptions down on a paper. So x of t less than or equal to a, and now our system h x of t is equal to e to negative absolute value t times a. Okay, now if we take the limit as t approaches infinity of this system, what do we get? Get e negative infinity a. So when it's negative infinity, it's just going to be 0, okay? And whenever t is going to be 0, it's going to give us 1. So this, the e, the factor over here, is always going to range between 0 and 1, and then is multiplied by a. So that's why it's always going to be a bounded output. So BIBO stable. Okay. Usually, you do need to interpret all the values of t. Okay, and in this case, we know that in the exponent, whenever it's 0 or whenever it's infinity, usually something happens, and that's why my method is to always take the limit as t approaches infinity. It's not a conventional method. You should check for all values of t, but usually checking infinity and 0 tells you a lot about the behavior of the function. So here, for the last one, let's do x of t less than or equal to a for the input. So the system of t is going to be equal 1 over t minus 1 x or a. Okay, here if we take infinity, we're gonna get 0 times a, which is fine, but we also need to check the root of this denominator. So when we have like th of 1, we're gonna get 1 over 0, which in signals and system, whenever you have the 0 in the denominator, it's always infinity. So infinity times a, which is not less than infinity, so it's not. So it's unstable. Okay, that's it for this video. Thank you for watching, and I'll see you in the next one.